Okay, great. So what I'll do now is tell you about some quantum games. Now, I should say right at the outset that I'm really not an expert in this area. This is something that I've learned over the years, but I have not actually worked on this area myself. But I find it to be a really fascinating subject, to be able to combine quantum mechanics and game theory. So I decided to prepare a talk on this many years ago, and so here it is. And as usual, here's my email address. If you have any questions, please do send me an email and I try to answer as best as I can. Now, there are several concepts from quantum mechanics that will appear in this talk, and most of them I've already discussed in my earlier talk this morning. So I may actually skip over those slides when I come to them. But of course, if something was not clear in the morning or if it's not clear now, you can ask me. You're most welcome to do that. So the outline of the talk is introduction to qubits, which I actually gave in the morning, and an introduction to game theory, a very brief introduction to game theory, in fact. Then I'll tell you about three different games in increasing order of complexity. So the first game is called the coin flipping game, and it turns out this is leads up to the subject of quantum error correction codes. So which I won't actually tell you about, but you'll see why this coin flipping game actually can be connected to error correction codes. The game two is something called cats and dogs questions, and this is related to something called the CHSH inequality, which is actually closely related to the Bell inequality that I talked about earlier. The third one is this very famous game called the Prisoner's Dilemma, which I'm sure you have heard in other talks, and you'll hear more in other talks in this workshop. But you'll hear it again very briefly from in the present talk. And there are two things that I like about this game, which is related to the concepts of Nash equilibrium and Pareto optimality. And then I'll tell you about a quantum version of the prisoner's dilemma. Okay, so qubit. So let me just go over this very quickly. So a qubit is basically a two-state quantum mechanical system. So we denote the two states as 1, 0 and 0, 1. We don't really have to know now what these two states stand for. One example that I gave in the morning is that if you take an electron which is spin half, then 1, 0 stands for a state where the electron spin is pointing up along the z-axis, and 0, 1 has the electron pointing down along the z-axis. But it doesn't matter what these two states stand for physically. It's just important that there are two states, and so the general state of the system is a superposition alpha beta. So alpha times 1, 0 plus beta times 0, 1. And we'll always fix mod alpha squared plus mod beta squared is 1, so that the total probability to find the system is in one of the two states is 1. So this is quantum mechanics. So alpha and beta are the amplitudes. You have to take their modulus squared to find the probability in being in those states. Okay. So an example of a qubit, as I already said, it is a spin half object. So that's a very quick introduction to qubit. And now here's a very quick introduction to game theory. So this is only something about game theory. I'll say more about game theory as we go along, but this is a very basic slide on game theory. So the subject probably began with this seminal work by von Neumann and Morgenstern called The Theory of Games and Economic Behavior, 1944. So here's a simple version of a game. So you consider a game with two players, 1 and 2, and there are many possible strategies that each of these players can adopt. Now, a given strategy, SI, which is SI1 and SI2, what this means is that I is the ith strategy, where the strategy of player 1 is SI1 and the strategy of player 2 is SI2. Now, given a strategy, there's a payoff to the players. The players are labeled as 1 and 2. So there's a payoff to the players 1 and 2, which are given by PI1 and PI2. These are, of course, real numbers. So you can think of payoffs as some money that you can get if you play the game in a certain way. The idea is that each player will try to maximize their payoff. Now, there are different kinds of games. The players may or may not cooperate with each other to maximize their payoff. So accordingly, you can have cooperative or non-cooperative games. A zero-sum game is one in which the sum of the payoffs is zero for all the strategies. What this means is that if player one gets a lot of high payoff, player two will get a negative payoff, so that the sum is zero. So here, of course, it's a non-cooperative game because each of them will be trying to maximize their payoff. But there are cooperative games which are not zero-sum, okay, where both of them can try to maximize the payoff, and they can even cooperate with each other to do that. Okay, so this is basically very simple notion of a game. Now, we'll consider situations where a game is played a very large number of times, and the payoff will then be defined as the average of the payoff, not playoffs, payoffs in all the games. Now, the reason for doing this is not very common in real life that you play a game, particularly if it's an important game like a football final. You, of course, don't play it more than once. But the reason we are going to consider games which are played a large number of times is to mimic something that we do in quantum mechanics. So in quantum mechanics, you make measurements many, many times because quantum mechanics is a probabilistic theory. And only if you make measurements many times can you average over them and thereby calculate the probability of a payoff. And you can compare that then with the probability that you get from taking the wave function modulus squared. Okay, so this idea of playing a game many times is really directly motivated by the situation in quantum mechanics, which is probabilistic. Now, the other thing about playing a game a large number of times is that this allows you to consider mixed strategies, where the players can randomly change the strategies from one game to the next, instead of only considering pure strategies where they make the same move in every game. Okay, so either they can make, so the simplest strategy would be they make exactly the same move in every game, but a mixed strategy is richer. You're allowed to change your strategy from one game to the next. Okay. Then the next thing I've already said, quantum mechanically playing games a large number of times and taking the average makes sense because quantum mechanics is a probabilistic theory. So when we talk about quantum games, we have in mind that you're going to play a game many times and then take the average, and thereby, having one of the important features of quantum mechanics, which is probabilistic. Okay, so let me now turn to the first game. Now, the interesting thing about this area of quantum games is that it became very popular in the 1990s, and you will actually see a few FISREV letters on this, on the concept of quantum games. And thereafter, it seems to have kind of died off. Okay, so all the papers I'll refer to here, most of them will be from the 1990s, but they'll all be FISREV letters. Okay, so the first game called the coin flipping game is as follows. So there are two players, C and Q, which actually means classical and quantum. And you'll see that in the way they have their strategies defined. So then there's a referee. And what this referee does is that the referee takes a coin and places it head up inside a box. So the two players know that this is the coin is pointing head up and it's inside the box. Now they can't look into the box, but what they can do is as follows. So first, the quantum player Q can reach into the box and do something to it without looking at it. Then the classical player can either flip or not flip the coin, again without looking at it. So it just reaches inside the box and either doesn't do anything to the coin, takes out the hand, or just flips over the coin and then removes the hand. Finally, Q does again something to the coin without looking at it. So at no stage do the players look at the coin, but they can do something to it. Now the box is opened. The referee opens the box and looks at the state of the coin. And if the coin is head up, then the referee says Q is the winner. And if the coin is tail up, then C is the winner. So this is clearly a zero-sum game, right? Both cannot win. If one wins, the other loses. So turns out that Q has a quantum strategy which always wins regardless of what C does. Okay. So if I don't tell you anything more, this sounds completely amazing that C can either flip or not flip, but Q can anyway win the game. So how is this possible? So here are the key points. So first of all, the coin is a quantum object. So straight away, we are talking of a very unusual coin. The head state H, let's call that 1, 0, and tail is T, 0, 1. The coin can in general be in the state alpha H plus beta T. Okay, so this is the column alpha beta. Okay, so it's a quantum coin. Secondly, the quantum player Q is allowed to make quantum moves on the coin. Now, what that means is that Q can act on the state of the coin with an arbitrary unitary matrix U. So as I discussed in the morning, unitary matrices have this property that when they act on a column, they don't change the probability, right? So if they act on a column alpha beta, then mod alpha squared plus mod beta squared remains the same. But alpha changes to alpha prime, beta changes to beta prime. Okay. So in other words, for example, if the coin is in the state 1, 0, Q can turn it into a state which is 1 by root 2, 1 by root 2, right? It's equal superposition of head and tail. So this would of course make no sense in a class for a classical coin, but let's say this is the rule of the game for us. On the other hand, the classical player can only flip or not flip the coin. Okay, so these correspond to acting on the coin with either a matrix F, which is 0, 1, 1, 0, which is actually one of the Pauli matrices, sigma x, or N, which is 1, 0, 0, 1, which is the identity matrix. Okay, so it's easy to see that when F acts on 1, 0, it turns it into 0, 1, or if it acts on 0, 1, it turns it into 1, 0. So F is the flip operation. It changes head to tail or vice versa. Whereas N stands for not flip. So it just keeps the coin as it is. Now, these two matrices, of course, commute with each other. That's easy to see. And that's the sense in which we say that the strategies of C are purely classical. So the idea is classical operations always commute with each other. So operations not commuting with each other is one of the characteristics of quantum transformations. Okay, so Q's winning strategy is now as follows. So first, remember the rules was that Q does something first, then C can either flip or not flip, and then Q again does something. So in the first step, Q acts on the coin with this unitary matrix, which you have seen in the morning. So it's U 1 by root 2, 1, 1, 1 minus 1. So if suppose the coin started out as head, that was the initial condition. So under this move by Q, the coin changes from H to UH. Now C, of course, can act on this with either the flip matrix F or the no flip matrix N. And so depending on what C chooses, the state of the coin becomes FUH or NUH. So I hope the notation is clear. F and U are matrices, whereas H is just a column, 1, 0. The last move is Q's. So Q again acts on the coin, but this time with the matrix U dagger, Hermitian conjugate of U, which is also the inverse of U. It's a unitary matrix. And so the state of the coin after that move is U dagger FUH or U dagger NUH. Now, given the forms of F, N, and U that I've shown you, you can verify that U dagger FU is 1, 0, 0 minus 1, and U dagger NU is identity. And you can see that both of these acting on H gives you H. Okay, so no matter what C does in the middle, either flip or not flip, if you start with the head state 1, 0, it remains 1, 0. Okay, so the fun thing is that the coin always ends with head up, no matter what C does in between, and Q wins. You can ask what will happen if the initial state was not head but tail. Then you'll discover that if it started as tail, then U dagger FU will turn it into minus tail. But that's really the same as tail in quantum mechanics, because in quantum mechanics, you only calculate probabilities, not the wave functions themselves. So again, if you start with the coin in the tail state in the beginning, it will remain in tail state as far as the probability is concerned. Okay, so this is the first game where regardless of what C does in the middle, the player Q has a strategy which will always win. So this matrix U that appeared is sometimes called the Hadamard matrix in the community on quantum information or quantum computation. It basically transforms from the sigma x basis to the sigma z basis. And so it corrects a flip from up to down in the sigma z basis, which is called a bit flip. This flip from 10 to 01 is called a bit flip, because that's what classically 10 and 01 are 2 bits, and this is flipping between them. Now you can see this is also the simplest example of a quantum error correction code. Namely, you're sending a signal. The signal can be either up or down, or 10 or 01. Someone in the middle can just arbitrarily flip this signal to the opposite state. But by acting first on the signal with Q and then acting first on the signal before you send it with U, and then after you have received it at the other end, you act on it with U dagger. By doing this, you can correct for any arbitrary flips that happened in the middle. Okay, so this is actually the simplest example of error correction code. There are more complicated codes which correct a sign flips. Okay, so what I told you about is a bit flip, where you suddenly flip from 10 to 01. You can also flip from 10 to -10, or 01 to 0 -1. That's called a sign flip. And there are codes for correcting that as well. And there are more complicated codes which can correct for a combination of both bits and sign flips. So if you want to know more about this, you're welcome to look at this paper from 2019. The reference is here. Okay, let me pause here. Are there any questions at this stage? Okay, so if not, let me go on to the next game. So the next game is a little more complicated, and it's called the cats and dogs game. So again, there are 2 players, and you'll see that this is going to be a cooperative game. So both the players they can try to cooperate to win, for both of them to win as far as possible. So the rules are as follows. So once again, there's a referee, a third person, and this referee asks each of the 2 players with probability half, do you like cats or do you like dogs? And each of the players has to answer yes or no. Okay, so the referee asks player 1, do you like cats? And the player has to say yes or no. Or the referee can ask, do you like dogs? And the player has to say yes or no. Then the referee goes to player 2 and again asks one of the 2 questions. And player 2 also has to say yes or no. And the referee can switch around the questions. So sometimes the referee can ask about cats, sometimes the referee can ask about dogs in a random way with probability half each. It's important that the players know that the probabilities are half each, because it turns out that the strategy depends on that. If the probabilities were 3/4 for cats and 1/4 for dogs, the strategy would have to be changed a little bit. Okay, so this is about asking the question and the players giving some answer. Now the payoff is like this. If either player or both of them is asked the cat question, then they win 1 point each if they give opposite answers. And they get no points if they give the same answer. Okay, so this sounds a little complicated. So let's say both of them ask the cat question and one says yes and the other says no, then they win 1 point. But if both of them say yes or both of them say no, then they get no points. On the other hand, if they both ask the dog question, they win 1 point if they give the same answer, and they get no points if they give opposite answers. Okay, so this is a bit sounds a bit complex, so you really have to sit down with this and think about it a bit. Now the rule is that these 2 players can decide on a strategy right at the beginning, okay, before all this has started. But once the thing has started, they can't talk to each other anymore. Okay, and remember, these games are going to be played many times, so they can only decide on some strategy at the beginning before the first game, but not after that. And then the game just goes on hundreds and thousands of times, let's say. Okay, now let's look at an example of a strategy. So one strategy could be that they decide in the beginning that they'll always give opposite answers. So player 1 always answers yes and player 2 always answers no. Then if they randomly ask the cat and dog questions, they will win 3/4 of the time and lose 1/4 of the time. Okay, why is that? So let's go back. So remember, the rule is that if either or both of them is asked the cat question, they win 1 point if they give opposite answers. So if they ask cat or cat dog or dog cat, they win 1 point if they give opposite answers. Only if they are both asked the dog question, then they get no points if they give opposite answers. So if they randomly ask the cat and dog questions, they'll win 3/4 of the time and lose 1/4 of the time. So the expected payoff in the long run is 3/4. So it turns out that this is the best possible expected payoff if they're restricted to classical strategies. Notice that this is still a probabilistic strategy classically, because I mean, their strategy is not probabilistic, but they can be asked the questions in a probabilistic way. Okay, so best classical payoff 3/4 or 0.75. Turns out that there's a cooperative quantum strategy which does a little bit better. So how does this go? Okay, so now this is a complicated story. So the quantum strategy is that before each game, there's a friend who produces a singlet state using two spin half objects and gives these two objects to the two players. Now, singlet, so this we saw in the morning. The singlet is made out of two spin half objects, and it has a wave function which is a superposition of the following form. It can be in the state 1, 0 times 0, 1. So for player 1, it's 1, 0. For player 2, it's 0, 1 with an amplitude 1 by root 2. Minus state in which player 1 is 0, 1 and player 2 is 1, 0, again with 1 by root 2. Sorry. So it turns out that this is what is called an entangled state. So a measurement of the component of the spin in any direction for the first object will give either up or down with probability half each. And as soon as the player 1 knows what the component of the spin in any direction is for that player, the player immediately knows what is the component of the spin for the other player. So this is the hallmark of an entangled state, that measurement by one player on their own spin immediately tells that player what the state of the other player's spin will be. Okay, so let me say that again. So if player 1 measures along the z-axis, z direction, and finds 1, 0, then player 1 immediately knows that player 2 will find 0, 1. Now, instead of measuring along the z-axis, they can measure the component of the spin in some other direction. What is the story in that case? So in that case, what happens is the following. So if player 1 measures the component of the spin in some particular direction, could be z, and finds some value, and player 2 measures the spin in some other direction, which is not z or minus z, but is some arbitrary angle theta with respect to the first direction, then the second player will find the opposite value of the spin with probability cos squared theta by 2. So where did this come from? So this comes from the following fact. I discussed this in the morning. If a direction in 3 dimension has this polar coordinates theta phi, so theta is the angle between this direction and the z-axis, then the wave function of a spin half object whose spin component in that direction is given by h bar by 2 is cos theta by 2 is the upper component and sin theta by 2 e to the I phi is the lower component. From this, we can show that if one of the two objects in a singlet has a spin pointing along the z direction, then the probability that the spin of the other object will point in the same direction is sin squared theta by 2, or opposite direction is cos squared theta by 2. Okay, so the players know all this. We assume these players know all about entangled states. So the quantum strategy that they decide amongst themselves right in the beginning is the following. That they choose 4 directions lying in a plane, which I'll call 2D, 1C, 2C, 1D. These are some fixed directions that they decide on in the beginning of the game. If player 1 is asked the cat question, he will measure the spin of his spin half object in the direction 1C. But if player 1 is asked the dog question, he'll measure his spin in the direction 1D. Similarly, if player 2 is asked the cat question, she'll measure the spin of her object in the direction 2C. And if 2 is asked the dog question, she'll measure it in the direction 2D. So we take these 4 directions to lie in a plane with the relative angles alpha, beta, gamma, and they're fixed by the players in the beginning. And we'll see how they have to be fixed in the next slide. Now, in all cases, the player answers yes if they find the component of the spin to be plus h cross by 2, and no if the component is minus h cross by 2. Okay, so with this above strategy, you can show that their expected payoff in the long run is as follows. It's 1/4 cos squared alpha by 2 plus cos squared beta by 2 plus cos squared gamma by 2 plus sine squared alpha plus beta plus gamma by 2. Okay, first of all, why is there a factor 1/4? And that's because they can be asked 4 different questions with probability 1/4, right? Because the probability of cat or dog is 1/2 for each player, and there are 2 players. And where do these cos squares appear? So you can see it from here. So there is this angle alpha. So if player 1 chooses strategy 1C and player chooses strategy 2D, the payoff will be cos squared alpha by 2. Similarly, something else will give you cos squared beta by 2, cos squared gamma by 2. And then the angle between 2D and 1D is alpha plus beta plus gamma, and cos squared of that is sine squared of alpha plus beta plus gamma by 2. Okay. So what we do now, so there are these 3 angles, alpha, beta, gamma, to play with. And so what you can do, you take this expression for the payoff and maximize this with respect to these 3 angles. And you find that it's maximized when all the angles are equal to pi by 4, 45 degrees. And then the expected payoff is cos squared pi by 8, which is, it has an exact value, half plus root 2 by 4. So it's roughly 0.8536. So notice that this is better than the best classical strategy, which gave 3 by 4. Now it turns out that this cos squared pi by 8 is actually the best that a quantum strategy can give. And this was actually proved in this paper by these 4 people. So this is actually called the CHSH inequality, named after these 4 people, Clauser, Horn, Shimoni, and Holt. This is actually a very old paper, 1969. Now, this game shows something very interesting, that 2 players who possess 2 kinds of a quantum entangled state have access to some kind of shared information which has no classical counterpart. Okay, so it's very hard to put your finger on where exactly did they share the information. You can't really answer the question in a simple way. But they shared the information simply by virtue of the fact that there's a third person who produced a spin singlet state and then gave one out of those 2 spins to player 1 and the other spin to the other player. And just this act of sharing a spin singlet state gives them some extra resource which doesn't exist classically. Now, an interesting thing is that there are actually 2 different inequalities showing up here. So the first one is that classical strategies have a payoff which must be less than equal to 3/4, as we saw. Quantum strategies can violate this inequality. You can get a payoff which is bigger than 3/4, but it can't be arbitrarily big. It must be less than this number, 0.8536. So the first inequality where quantum mechanics can violate a classical bound is called a Bell inequality. And the second inequality, which even quantum mechanics cannot violate, is called a Cyrilson bound. So this was proved by Cyrilson many years after Bell. Now, okay, let me just go through this. So this was for the case of spin half. So just out of curiosity, I decided to check out what happens if you take a higher value of the spin. Spin is an intrinsic property of particles in quantum mechanics, and particles can have spin half or spin 1 or spin 3/2 and 2 and so on. And so in principle, you could have taken 2 spin 1 objects or 2 spin 2 objects instead of spin half. And then if you play the same game with the same kind of rules, which I won't get into now, but very similar rules, that if you measure the spin in some direction and get a positive value, then you have a payoff. According to that, if you get a negative value, you get a different payoff. If you play the game, you discover that in the limit that S goes to infinity, the best payoff for this quantum spin S objects becomes 3/4. Okay, so there's a plot here to show that, but let me not go over this. The main point about this slide is that even though spin is a quantum mechanical property of objects, the limit in which the spin S goes to infinity is actually a classical limit. So in that limit, your quantum mechanical results all turn over into classical mechanics results. And so this is actually always an interesting limit to check. When you do a quantum problem involving spins, you can always check what happens if S, instead of being half, is taken to have a very large value, like 100 or 200. And if things work out properly, you should find that you get the classical result in that limit. Okay, now I think I'm going to skip this part about Bell inequality because I discussed this in the morning. So let me just pause here and see if people have any questions so far. Doesn't sound like anyone has questions. Okay. So I'm skipping over the Bell inequality, violation of Bell inequality. Okay, so I'll come straight to the third and last game, which is called the prisoner's dilemma. Okay, now as I said, I went through the program of the workshop and I found that people are talking about this. In fact, there's one set of talks which discusses many cases involving prisoner's dilemma and generalizations of it, and there'll be other talks on prisoner's dilemma. So what I'm going to say will not be really new for you, but this is just my take on it. Okay, and I guess it doesn't hurt to repeat things. So here goes. So we have a game between Alice and Bob, two players, A and B. So Alice and Bob are often names given to quantum players. Okay, and they're chosen so that one is A and one is B. And they have two possible strategies, C and D, and there's a payoff table given here. Okay, so so you read the payoff table like this. So if Alice chooses strategy C and Bob chooses strategy C, each of them gets 3 points. If Alice chooses strategy C and Bob chooses strategy D, then A gets 0 points and B gets 5 points, and so on. There's a story where this comes from, where this kind of payoff table comes from. So let me tell you the story. So suppose you take these numbers that you see in the table at the top, and you subtract all these numbers from 5. Then you get a new table, which is shown below. And think of this table as the number of years that two persons would be in prison for some reason. Okay. So the idea is that there are two prisoners. They're interrogated independently by police. So the police put them in different rooms, and so that they can't talk to each other. And the police ask them, did you do this crime or did you not do this crime? So the police have a suspicion that they both participated in the crime, but the police are not absolutely certain. So that's why they're interrogating them. So the two prisoners, they can decide right in the beginning, before they're put in separate rooms. They can decide right in the beginning that they'll always cooperate with each other. So they'll both tell the police, we did not commit this crime. Neither of us committed the crime. Or once the questioning starts, they can defect. In other words, player A, when they're asked, did you commit the crime? Player A can say, no, I didn't commit the crime, but the other player did commit the crime. Okay, so there is different strategies where they try to save each other, or they try to save themselves and not save the other one. And depending on all this, they can have to spend so many years in jail. Okay, so you can see that this payoff table, the lower one and the upper one, they're just related by, one is the inverse of that, of the other one. Okay, so I'm sort of glossing over this because I'm sure this has been explained to you in a different set of talks. So let's return to the payoff table, which looks like this. Now, what is very strange about this problem is the following, which is that in the language of game theory, the strategies ACBC, ACBD, and ADBC. So that means the top entry, okay, let's say the entry 330550 are what are called Pareto optimal. Okay. And the last strategy, ADBD, 1-1, is at a Nash equilibrium. So I have to explain these terms to you. What is Pareto optimal and what is Nash equilibrium? And why should you care about whether something is Pareto optimal or Nash equilibrium? Okay, so a little bit of a story then. Who was Pareto? So Pareto was Italian sociologist and economist. Lived a long time ago, more than 100 years ago. He is actually credited with turning economics into a quantitative field of research. So apparently before him, economics papers were more philosophical papers rather than quantitative subject. But he developed economics into something that you can analyze numbers, graphs, and so on, statistics. The other thing is known about is something that you may have heard of. It's called 80-20 observation. It's called the Pareto principle. So the Pareto principle is the following, that he noticed that in Italy at that time, 80% of the land is owned by 20% of the families. So obviously a very unequal society, but there are many societies like that even today. But this kind of a unequal um, distribution occurs in many, many areas of life. So as an example relevant to scientists, something like 80% of the citations will be cornered by 20% of the scientists. Now, it doesn't have to be 80-20, it can be 90-10, it can be 70-30, but it'll always be unfair, or I shouldn't say unfair, always be unequal. Okay, so this kind of thing is called Pareto principle, and it's a basic feature of life. Okay, now let me tell you what a Pareto optimal strategy is. So a strategy is called Pareto optimal if there's no other strategy in which at least one player has a higher payoff and no one has a lower payoff. Okay, in other words, we call a strategy Pareto optimal if you deviate from that strategy, at least one of the players will be worse off. Okay. Now, depending on the rules of a game, it may have no parity optimal strategy. That's possible, or it may have more than one parity optimal strategy. Okay, so let's go back to the payoff table. So this 3, 3, 0, 5, 5, 0 all Pareto optimal. Why is that? Because if you move away from 3, 3 to 0, 5, then player A is worse off, right? It's going down from 3 to 0. So 3, 3 is certainly more optimal, Pareto optimal than 0, 5. For the same reason, it's more Pareto optimal than 5, 0. And of course, it's much better than 1, 1, where both players are worse off. Okay, so these three here are Pareto optimal, and 1, 1 is not Pareto optimal. 1, 1 is not Pareto optimal because you can move from that to any of the other three, and well, you can move from 1, 1 to 3, 3, and both players will be better off. So 1, 1 is clearly not Pareto optimal. Okay, so that's Pareto optimality. Now, let me just say a few words about Nash equilibrium. So this was introduced by John Nash. Nash was actually a famous mathematician, and the work he did in game theory, Nash equilibrium, is only one of the many things he did. He made many contributions to basic pure maths, but he's probably most known for Nash equilibrium, and eventually he got the Nobel Prize in economics for this. You may have actually seen a movie by him called A Beautiful Mind. He's a very interesting person, passed away a few years ago. Okay, so we say that a strategy is at a Nash equilibrium if for each player A, there is no other strategy which increases the payoff of that player, assuming that the other player holds their strategy fixed. Okay, so let me say that more carefully. There are two players, A and B, and the idea is that A doesn't know what the strategy of B is going to be. Okay, so A is completely blind to what B is doing. So A just thinks from their own point of view. What can I do to maximize my own payoff? So if you find that there is nothing you can do to maximize your own payoff, and this is true for both player A and player B independently, then you say that you are at a Nash equilibrium. So a game may have no Nash equilibrium or may have more than one Nash equilibrium. So let's go back to this payoff table. So I've already explained why three of these are Pareto optimal and the 1, 1 is not Pareto optimal. On the other hand, if you look at the concept of Nash equilibrium, you can see that 1, 1 is at a Nash equilibrium because why is that a Nash equilibrium? Because let's say, okay, let's start with 3, 3. Okay, so let's look at things from the point of view of player A. Now, player A doesn't know what player B is going to do. So let's say we are in the first column, right? Now, so B has adopted a classical strategy C. So the payoffs are 3, 3, and 5, 0. Now, So if you're at 3-3, then you can certainly improve A's payoff by going to 5-0, right? So this is not an equilibrium. Similarly, if you're in the second column, which is 0-5-1-1, if you're at 0-5, you can increase A's payoff by going from 0-5 to 1-1. Okay. Now B has the same logic. So for B will also say that 3-3 is not a Nash equilibrium because I can improve my payoff by going from 3-3 to 0-5. And similarly, 5-0 is not a Nash equilibrium because I can increase my payoff from 5-0 to 1-1. Okay. So only 1-1 is a Nash equilibrium for both the players. So now you see there's this tension that three of the strategies are optimal in some sense, but they're not at a Nash equilibrium, whereas the one which is at a Nash equilibrium is not optimal. So the upshot of all this is that if each player independently found their best strategy, each of them would choose the last one, which is ADBD. Both of them choose strategy D. On the other hand, if they agreed that the cooperative strategy is the best, then if in the beginning, if they knew the payoff table in the beginning, they would agree that the cooperative strategy is best for both of them simultaneously, 3-3. Okay. So this is an example of a game where cooperating with each other gives a better result than each of them choosing a selfish strategy where you don't care about what the other person is doing. Now, as you know, this actually has a lot of real life applications, particularly if you think of two countries which have nuclear weapons, and they think they benefit by having more and more nuclear weapons because it gives them more security. On the other hand, they lose money making all these nuclear weapons, the money that they could have used for something else. And so there's a payoff. And so if they don't trust each other, then they'll spend a lot of money on nuclear weapons and then not be able to spend that on more important things. And so they'll lose overall. Whereas if they really trusted each other and discussed with each other, they would decide that there's no point having nuclear weapons. We are never going to fight a nuclear war, and they would choose to spend the money on something else. So that's a real life example of a prisoner's dilemma, which had some role apparently in the Cold War between the USA and the USSR, as it was called then. Okay, so that's about the prisoner's dilemma. So everything so far is classical. So what this paper in 1999 set out to do is, can we think up of a quantum version of the prisoner's dilemma game, which has a different solution where Nash equilibrium and Pareto optimal actually coincide. Okay. So in general, it's a good idea to have a game where Pareto optimal and Nash equilibrium coincide because then they're kind of consistent with each other. Okay. You can't improve things further and you don't make things worse by sitting at that particular point. Okay, now I'm going to go over this game a little quickly because it's rather complicated. You're welcome to read this paper if you want to really understand this game. So I'll just describe it very briefly. So the state space, so again, this is going to be a quantum version. So you have four possible states. So the state space is four-dimensional, and the superposition of different strategies is allowed. So immediately that makes it a quantum game that you're allowed to superpose different strategies. So the four strategies, as we have seen, is AC, BC, ACBD, ADBC, and ADBD. Next, we consider some initial state, and then you introduce quantum entanglement in some way. Now you want to have the classical prisoner's dilemma that I've told you about. You want to have that as a particular limit of this quantum prisoner's dilemma. So the initial state must be such that if no quantum entanglement is introduced, you recover the classical game. Okay, so there's an initial state with this requirement. Then each of the player independently makes an arbitrary unitary transformation on the given state, and I'll tell you what that unitary transformation is. And then the final state and the payoff table are used to compute the expected payoff of each of the players. Okay, so these are the broad ideas of this quantum version of this game. Okay, so details. So the basis states are C10 and D01, so cooperating or defecting. These are the basis states, so they're columns. You also have strategies which are matrices. The cooperative strategy is C hat, which is the identity matrix, and D hat, which is this off diagonal matrix 0, 1, minus 1, 0. It's actually I times one of the Pauli matrices. The players move, as I said, they can act with a unitary matrix. And the most general unitary matrix they can take is given here. Cos theta by 2 e to the I phi. That's the 1, 1 element. The 1, 2 element is sine theta by 2 and so on. So there are some special cases of this. For example, if you take theta equal to 0 and phi equal to 0, then you get the identity matrix C hat. Then if you take theta equals pi, then you get the defecting matrix D hat. Or you can take this interesting matrix Q hat, which is theta equals 0, but phi is equal to pi by 2. Okay, so each of these players can act with any unitary matrix. These are just 3 special cases. And then the combined strategy of the 2 players is given by direct product because they're acting on the state of the system independently. Player A uses unitary transformation UA, player B uses unitary transformation UB. Did I skip something? Okay. So let's start with the initial state in which the 2 players are cooperating with each other. So it's 1, 0 times 1, 0. Then you introduce quantum entanglement by acting on this with a matrix of this type. So it looks a little complicated. So I've simplified it. So this matrix J is cosine gamma by 2 times the direct product of 2 identity matrices plus I sine gamma by 2 direct product of 2 D matrices. Remember, D matrices are given in the previous transparency, previous slide, 0, 1, minus 1, 0. So this matrix J is chosen so that it's a 4 by 4 matrix, which is unitary. And gamma is an arbitrary parameter. It can take any value. Now, if gamma is 0, then you can see that J is just the identity times identity matrix. So it actually does nothing by acting on the initial state, C times C. So that just gives the classical game. On the other hand, if gamma equals pi by 2, then these 2 parts of J, I times I and D times D, each of them has a 1 by root 2. So you have an equal superposition of these 2 terms. So that gives you maximum entanglement. Next, the players are going to act with the transformation UA cross UB. And as I said earlier, UA and UB will depend on some angles, theta and phi. Actually, theta and phi for player A and some other angle, theta prime, phi prime for B. And then finally, we act with the dagger of J or inverse of J. Okay, so those are the rules. So the final state that you get is the initial state was 1, 0 times 0, 1. Then you acted with J. Then the players act with UA times UB. And then you act with J dagger. Now, if you denote the probabilities, the players will use the 4 possible strategies CC or CD, DC, and DD. So remember, C is cooperation, D is defect. Then the probabilities of players will use the strategies are obtained by taking inner products of C times C or C times D or D times C and D times D with psi. And then, so it's basically what is called an expectation value. So you have a psi as a row on the left, and then there is this where psi is given here. Then you act on it, follow that up with C times C or C times D, etc. And then again a psi. So an expectation value of the type that you calculate in quantum mechanics. And then you calculate the payoffs, SA and SB of the 2 players using this payoff table that we saw earlier. So we find that the final payoff, so this is the average payoff after many iterations of the game. SA is 3 times PCC plus 5 times PDC plus B times DD. Where did this come from? So you just look at the entries of this column of this table for player A. So for AC BC strategy, the payoff is 3, so that's 3 PCC. Then AC BD strategy is no, not AD-BC strategy is 5, 0, so that gives you this 5 PDC. And then AD-BD strategy is 1, so that's PDD. Similarly, there's a payoff for SB, the player B. Okay, so I'm just going to show this plot. Again, this is a lot to digest, I know. But what this plot shows you is that on one side, you have all the possible strategies of the player B, all the possible unitary transformations that player B can act on, UB. So that's this line. And on the other side, you have UA, all the possible strategies of A. And this is the picture if they play the classical game, gamma equals 0. So in this thing, you find that the maximum possibility for A is okay. So the height is telling you the payoff for player A, dollars. Okay. You find that this point, which was where they both use strategy D, as I said, it's a Nash equilibrium, but it's not parity optimal. The payoff is 1 for each player. So this we saw in the payoff table earlier for the classical game. But if you take an entangled initial state, then so you choose gamma equals pi by 2, then it turns out there's a better strategy where they both use Q. So Q was one of the matrices that I pointed out. So if they both act on the initial state with Q. So that's why it's Q times Q, Q for player A, Q times B. And then the best strategies, the best payoff for player A is at this point here, where the payoff for each of them is 3. Okay. And this is the best payoff for both of them. So just by changing the rules of the game, by choosing the initial condition in a different way, you have turned the game in a way so that now there's a point which is a Nash equilibrium as well as parity optimal. You can actually move along this surface and see that you can't do better than this, either in the Nash sense or in the Pareto sense. That's the best you can do. So as I said, you can look at this paper if you really want to understand this properly. So interesting thing about this is that they came up with a quantum version of the prisoner's dilemma game, where turns out that the Pareto optimal and Nash equilibria coincide. Okay, so let me summarize. So I discussed 3 games. The coin flipping game, where we saw that there's a quantum strategy which always wins. And so this acts like an error correction code. You get the same, you win regardless of what happened in between because of the classical move in the middle. Then there's a cats and dogs game where there's a quantum strategy based on a 2-spin entangled state, which does better than the best classical strategy. And this is related to the CHSH and Bell inequalities. And then there's the prisoner's dilemma, the most complicated game in this talk. This is a game in which Pareto optimal strategies are not at Nash equilibrium and vice versa. But a quantum version of this game, which includes some entanglement, can resolve the situation and give a strategy which is both Pareto optimal and Nash equilibrium. Okay, so let me end with some references. So the CHSH inequality, which is equivalent to the Bell inequality, is in this paper, 1969. Myers' paper is about the coin flipping game, and then Izard, Wilkins, etc., is about the prisoner's dilemma, quantum version. And then there's another paper which is talks about many of these ideas. The 5th paper is particularly interesting to me because it was actually written by an economist who took the trouble to learn quantum mechanics. And so this paper by Landsberg is a simple introduction to quantum game theory written by an economist. Finally, I'd like to acknowledge some colleagues in the Indian Institute of Science from whom I learned most of this stuff. So Apurva Patel, who is my colleague, Center for High Energy Physics, who has done a lot of work on quantum information, quantum computation, and so on. And Professor Anil Kumar in the physics department. He's unfortunately passed away a few weeks ago. So he used to have this NMR lab where his students would actually try out this quantum game. So using NMR, you can actually manipulate the spins of ions between 2 possible states. So each ion would be like a qubit, and they could do all of these things. They could produce entangled states of 2 qubits. They could make measurements, and then they could interpret the measurement in terms of some payoffs and so on. So I actually learned a lot by talking to him and reading the PhD thesis of one of his students. Okay, that's it. So I'll stop here. If there are any questions, I'll be happy to take them.
Thank you so much, Professor Shen. Questions?
So in the first, am I audible?
Yes.
Yeah, in the first quantum game that you had mentioned, what exactly is meant by a error correction code? Like, what is the
Oh,
error?
okay. So the idea is very simple. Um, so an error correction code is that you want to transmit a signal from, let's say, point A to point B. Okay. And let me go back to that slide actually. So let's say you have a signal which can be either in the state 1, 0 or 0, 1. Okay. So let's say you want to transmit the signal 1, 0 from point A to point B along some long line. But somewhere in the middle of the line, there can be some noise which can flip this thing from 1, 0 to 0, 1 or vice versa. Okay. And it's completely unpredictable. You don't know whether it's going to flip or not flip. So what you do is that before you start the signal propagating, you act on it with this matrix U that I showed. And then something can happen to it on the way to the other point, or something may not happen. But no matter what happens, when it reaches the other point, you act on it with the opposite unitary matrix, U inverse. And you find that if you send 1, 0, you'll always get 1, 0 at the other end, regardless of what happened in the middle. So that's called an error correction code, because the error would be something happening in the middle, the state of the signal flipping or not flipping. Let's say flipping, that would be the error. And so you're compensating that by doing these unitary transformations in the beginning and at the end. Okay.
Oh, okay.
So that's the meaning of error correction in this context. Now, this is actually the simplest version of an error correction code. So there are more complicated error correction codes which involve, say, 3 qubits. And they can correct not just flips from 1, 0 to 0, 1, but also sign flips. Okay, so that's why I've given you this reference. This deals with this tells you a lot about quantum error correction codes in general.
What could be any real life significance of the quantum PD?
Of the quantum what?
Quantum prisoner's dilemma. Any real life significance of it?
No, none at all. This is
Okay.
this is really a paper written just for the fun of it. So the idea was to take a well-studied game, very well known to game theorists, economists, and so on, and see if you could change the rules of the game in such a way that this Pareto optimal and Nash equilibrium coincide. So this is kind of a philosophical thing. You know, Pareto optimal is kind of a socialistic thing, that you want to have a strategy which you can't improve that. If you try to deviate from that, somebody or the other will be poorer off. So it's kind of a socialistic strategy. And Nash equilibrium is more of a selfish strategy. You're just trying to maximize things for yourself. So the best strategy would be something which is both, right? Which in which no one is really worse off if you deviate from the strategy, but also you can't improve things for yourself anymore. So it's nice to have strategies which are both Pareto optimal and Nash equilibrium. So prisoner's dilemma is the simplest game of that kind, where these two are different. So what these 3 people decided to do is to see if you can change the rules of the game using quantum mechanics so that the Nash equilibrium and Pareto optimal coincide. There's absolutely no real life example of this quantum prisoner's dilemma.
Diptimanda, probably what Saptarshi meant was, how do we classically interpret the solution in quantum PD? Is there any way to classically interpret it? Like, suppose someone wants to.
Yeah. So that's this. So you calculate this payoff, this expected value at the end. Okay, so let me get to that. Right. So so these 2 players, they can follow any one of these strategies, C or D, right?
Mm-hmm.
And depending on whether they both follow C or both follow D and so on, this is their expected payoff, right?
Right.
So it's 3 times this PCC, 5 times plus 5 times PDC plus 5 DD. This is the payoff in the long run, right? If they use these 2 strategies at random.
Right.
You want to see if you can maximize this.
Right.
So the idea is that you can maximize this if you start with an initial state. So everything depends on the choice of the initial state. If you start with the initial state which is not entangled, then you can't do better than the classical prisoner's dilemma.
Right.
If you choose a perfectly maximally entangled, in fact, gamma equals pi by 2, then the best strategy turns out to be one where you get a payoff of 3 for both the players. Okay.
Mm-hmm.
So payoff is just defined in the sense of this. It's the expected value of an operator essentially.
Right. No, so suppose one tries to play the classical PD with these probabilities, PCC, PCD, PDC, and PDD.
Right.
What would be the result? So
The result
like,
would be this first picture.
okay,
you
so
find-
okay,
So this is just showing one half of the picture. This is just the picture for player A.
right,
A different picture for the payoff of player
correct,
B.
yeah,
Now, if you just look at player A, then you recover the classical payoff table. So, for example,
Right.
if they both used a strategy D, they would each get 1 point,
correct,
right?
Yeah.
If they both used C, then I guess one of them will get 5 and the other one will get 0 and so on.
hmm
Right.
No, if they both play C, then both should be better off, right?
Right. So, but this is just the payoff for A. So if they
Yeah.
both choose C, then you're at some point in the middle of the
Yes,
picture.
yes,
But you can see that they're not both better off because so for A you get 5, but for B you have to look at the other picture which I have not shown here.
No, but since it's a symmetric game, presumably the other picture would also show for CC the same payoff for the other
No,
player.
but this surface that I'm showing you here is not a symmetric looking surface.
No, that's right. But for the point CC, the payoff should be the same for both players because it's a symmetric game.
Let me see that. So what was CC? CC was 5-5, right? No, 3-3, sorry. Let me go back. So if they're both using C, then that's correct.
Yeah, both should end up with 3.
You will see C. You'll see payoff for A is 3. Then you
Yeah.
have to look at the other picture.
Yeah.
And again, you'll see a payoff of
You
3
see
for
3. Yes.
Yeah.
And you have this Q now. So for Q also the payoff, if both play Q, so then
Yeah,
also
then-
they get payoff of 3. Is that right? For Q. Is that Q or?
I don't know actually. Let me see. I can't see it from this picture actually. If they both use Q, so that's somewhere in this corner.
Yeah. So it looks like that will also give 3, right?
Probably, but I'm not 100% sure actually.
Right. Okay.
This top is 5.
Yeah.
And so 3 is somewhere here. So I
Right.
don't. Yeah, it looks like we'll get 3 for both of them.
Yeah. Okay. But now when the game is entangled, then in principle it's possible to do better than the classical CC. Is that the point?
No, so if the game is entangled, then you actually get the Nash equilibrium is when they both get Q. And so the payoff is 3 for A, and then the similar picture for B will show 3. Okay, so I'm not 100% sure what the Q is and
Okay.
what the payoff is for the classical case,
Sure.
unentangled case,
Yeah.
where they both play Q.
Right.
Yeah, I'm not very sure about that. So you see, so what is worrying me is that in this picture there's this point where A plays Q. Oh, A plays Q and B plays D. So that's very bad. If A plays Q and B plays Q, then you're somewhere here. Yeah. Yeah, so it looks like it also gives 3-3. Yeah,
Right.
but then you have to look at what happens if you move away from that point.
Correct. Yeah.
That's where this concept of parity optimal
Correct.
Nash equilibrium comes in.
Yeah.
So if you move away from that point,
So So then A can get 5 by unilaterally deviating.
Yeah. And then in the other
Hmm.
picture, which is not shown here, B will get
Yeah.
0.
Correct.
Yeah. Whereas in the next picture, if you deviate, QQ is here.
Yeah.
You can see that no matter which way you deviate, the payoff becomes worse for both of them.
Correct. Correct. Yeah.
Yeah.
I'm actually quite confused about this quantum version of the prisoner's dilemma. In normal classical prisoner's dilemma game, there are these mixed strategies that one can write down. The C and D's are the pure strategies, but you
Right.
can play cooperate with certain probability and play defect. So is that something that is something similar happening here when you are in the quantum version? You are using these matrices for strategies and then manipulating them by acting on it by the unitary matrices, and some sort of superposition of strategies is
No,
occurring.
I don't think this. So I don't think mixed strategies are taken into account in this paper. So it's just player A can choose any one of these strategies, and player B can choose any one of these strategies. The strategies are just parameterized by this matrix U, theta of phi, and each of them can choose any one of these U's. They don't have to follow a mixed strategy. I mean, so the mixed strategy is actually not considered in this paper at all. So they just choose some particular strategy.
But what is Q then? I mean,
So Q is some okay. So Q is something that you can't call it either cooperate or defect, right? It's a very weird strategy. So you're acting on the state 1,0 with an I and a state 0,1 with a minus I.
so wouldn't you call
So-
it some sort of a mixed strategy?
No, not really. Because C is also the strategy C is the same way, right? You act on 1,0 with 1 and 0,1 with 1.
Hmm.
And Q is you just change the phases. You have opposite phases for 1 and 1,0 and 0,1. Yeah, it's not a mixed strategy in the sense that they're not really tossing a coin to decide which U to act with.
Yeah, that is true. But I mean, it's just a superposition of these pure C and D matrices, right? So that in that sense.
Actually, it's not, right? You can't write Q as a superposition of C and D.
You cannot? Minus I, okay. Okay.
Yeah, because C is identity, D is Pauli matrix sigma Y times I, and Q is Pauli matrix sigma Z times I. So they're actually really independent matrices.
Okay. Okay. Yeah. Thank you.
Yeah, so I agree. I mean, I also don't fully understand what's going on in this particular game. But it just looked interesting that you can change the rules of the game in quantum mechanics and get a different best strategy.
So would entanglement here correspond to communication in the classical game? Would that be the analogous?
Yes. No, so entanglement here, it's sort of analogous to entanglement of two spin halves. So it means that, so if you look at, okay, let's go back. So you're acting with this matrix J, right, on the initial state. So initial state is 1,0 times 1,0. So if you like, spin up times spin up. Now, when this J acts on it, it produces a superposition of two states. So which is spin up times spin up with cos omega by gamma by 2. Or what does D do? D actually flips it, right? D flips both of them, right? So what D does is that it flips both of them to down. Okay, so let me put it like this. So once J acts on this, your state, the 2-qubit state is spin up plus I times spin down, okay? So instead of being up, down, minus down, up, which I had in the spin singlet case, here I have up plus down, down. This is also an entangled state. And it has the same properties that if player A measured their spin, they would immediately know what the spin of the other player is. But if before making any measurements, they can only say with probability half what their own spin is. So it's exactly the same kind of an entangled state, but it's just a different entangled wave function.
Right. So in both these situations, the extent to which the states are entangled gives you some proxy for how much communication there is between the two players indirectly.
I would say there's actually no communication. So that's the point about having an entangled state, that they're not communicating in a classical sense.
Compare it with the
They're sharing this entangled state, and somehow that gives them access to some information. But that's not quite the same as communicating.
Right. But if I was forced to build a classical game which was analogous to this, communication would be the only way to
Right.
make them
Right.
comparable, right?
Yeah, right. But that's the whole point of this
Right.
this idea of entanglement, right? That you have an entangled state, and then you can imagine that the two parts of the system are sent to two people who are very far from each other, so they can't communicate with each other. Okay, they're separated by a distance so large that even if they send signals at the speed of light, it would not reach them before they make their measurements. Right. So in that case, so what I'm saying is that you can't really call this communication.
Right. No, I'm just okay, what I'm trying to get at is, could you look at the extent to which they're entangled, and does it say something about the classical version of the game? Like how much communication is necessary to make the Nash equilibrium and coincide with the Pareto strategy? Is
Oh, I
there
see.
some optimal amount of communication that you can?
Right.
Okay.
No, but the problem is that if they were really allowed to communicate with each other, that would actually change the prisoner's dilemma game completely, right? The idea of prisoner's dilemma is they're kept in separate rooms and they cannot communicate with each other. If you allowed them to communicate, I mean, they could do much better than
Right.
the standard prisoner's dilemma, right?
Right.
So you're asking a question, a very interesting question actually. So if you could dial up the amount of communication, right, from zero
Yes,
to
some sort of a
other
partial communication. Yeah.
partial communication, then at what point would let's say Pareto optimal and Nash equilibrium merge? Right, you're asking a question like that. So I don't have the answer to that.
Right. Okay.
But the point here is that they are acting independently with these matrices UA and UB, right? So the fact that they're acting independently is like saying that they don't consult each other, right? Just each of them just chooses some unitary matrix and acts with that.
So Diptiman, I mean, this question of Harish's actually just made me think of something. So, I mean, the concept of entanglement is that the states are somehow correlated.
That's right.
Yeah. So Sashi actually has this another solution framework called the coaction framework,
Okay.
which kind of argues that Nash is somewhat not exactly following its own axioms, in the sense that if every agent knew the fact that they are playing this game, that the payoff matrix is available, and they each knew that the other knows all the information about it, then actually they would go about playing a strategy which is in some sense unique. And so the question is only, what is this strategy? So in some sense they're bound to, I mean, even if the strategy is initially unknown, each would be playing a strategy which has to be the same and unique for the two of them. And from this, essentially, some fairly interesting consequences follow. So in the coaction framework, for example, agents are much more likely to cooperate with each other than in the Nash framework. So we have never actually seen it in this framework of correlation, but when we were trying to see how to interpret in terms of biology, we found that actually there are very interesting experiments where if two individuals come from the same culture, so they have shared values, they are way
Right.
more likely to cooperate than otherwise. And so we kind of interpret it as, in some sense, a shared culture. So they're not communicating, but they have a same value system, and so therefore in some indirect sense their decisions are correlated. So I'm just wondering whether that would be the classical analog of this entanglement. I mean, in the sense of something which just enforces correlation in the behavior of the two agents.
Right. Yeah,
And it's a fairly interesting thought. I mean, I don't know whether there's
that's true.
any basis to this, but I'm just thinking aloud.
Yeah, so I can see that. I mean, for example, suppose they're these prisoners are naturally nice people, nice to each other, and they decide that no matter what, we are just going to cooperate with each other, and we are
Mhm.
not going to give the police any information. Right? Then, without any more thinking, they would both pick the strategy C, right?
Yeah.
And the payoff would be 3-3.
Yeah.
Whereas if they come from a culture where they really distrust each other, then they would pick D
Yeah.
and D and
Yeah.
get 1-1. Yeah. Yeah. So it is possible that they decide a strategy beforehand. But I think the point is that this payoff table is fixed by the police, who's
Yeah.
captured these two
No,
people.
sure.
And in the beginning, before they're separated out into different rooms, they are
Yeah.
not told the payoff table before that.
Sure. No, I mean, so the coaction does not depend on them knowing beforehand what is the strategy. So the coaction basically says that it's just a common set of shared values, which is enough to, in some sense, making sure that they will come up with the same strategy. And so the interesting part is the strategy actually is not CC. The strategy is a mixed strategy, which as you gradually increase the temptation to defect, tends to probability of cooperation being half. So it's not actually they're doing CC.
Okay.
So it depends on the temptation to defect payoff also.
Okay.
Anyway, yeah,
But
sorry.
then this gets into the thing of repeated games, right? So
No. This is a one-shot
Then?
game. This is a
it's a
one-shot game.
one-shot game?
Yeah.
Okay.
I'll send you the paper across. Maybe if
Okay.
you just take a look and let me know your comments, it will be great.
Sure.
Okay.
Yeah, I'd be happy to look at it.
Sure.
Yeah.
Okay, if there are no more questions or comments, let's thank Professor Shin once more.
Thank you.